Evaluating the extraction of pedestrian pathway networks from multi-city imagery is a complex task, hindered by the variability, narrowness, and frequent disconnections of these pathways. To address this challenge, the paper introduces PathwayBench, a novel benchmark dataset comprising 3,000 square kilometers of land area across 8 cities, accompanied by manually vetted ground truth annotations. This dataset enables the evaluation of pedestrian pathway network extraction methods in terms of routability and downstream utility. The authors propose a family of evaluation metrics that move beyond simple edge counting, focusing on connectivity, degree centrality, and betweenus centrality at the scale of individual intersections. These metrics provide a nuanced understanding of the strengths and weaknesses of existing methods, revealing challenges and opportunities in computer vision and machine learning. The study demonstrates the effectiveness of PathwayBench in surfacing issues and opportunities in pedestrian pathway network extraction, emphasizing the importance of addressing these challenges for city planning and wayfinding applications. By computing metrics at the intersection level, the benchmark can identify subtle differences in pathway representation that are critical for real-world applications. This work highlights the need for more accurate, complete, and routable graph representations of pedestrian pathways, paving the way for future research in this area. PathwayBench is a comprehensive evaluation framework for the pedestrian pathway inference problem, which aims to produce a routable pedestrian network graph from co-registered aerial images, street map images, and road networks. This work addresses the challenges of extracting pedestrian paths, including inconsistencies in path widths, interruptions, and less reliable ground truth due to human mapping errors. The dataset includes regions from 3 cities: Seattle, Portland, and Washington, D.C., each with 5 co-registered features: aerial imagery, road networks, and human-validated pedestrian pathways. The evaluation procedure consists of standardized metrics for both rasterized annotations and pathway graphs, along with a novel traversability metric that captures global routability in a local, efficient computation. This metric exposes quality issues in extracted graphs that conventional edge-counting metrics do not, providing a better basis for assessing utility for downstream applications. The contributions of this work include a human-validated ground truth pathway graph for 3 city regions, co-registered rasterizations of these graphs to support the evaluation of segmentation-based vision methods, and a set of evaluation criteria emphasizing graph connectivity. The paper also presents an evaluation of state-of-the-art methods for the pedestrian pathway extraction problem, demonstrating that the diverse dataset exposes unique challenges and that the proposed metrics expose quality issues correlated with downstream utility. The paper is organized into sections discussing related work: the PathwayBench dataset, metrics for partition-level graph routability analysis, experiment results, and conclusions. In the realm of street and road network mapping, numerous studies have leveraged aerial imagery and auxiliary data to extract roads. For instance, Wu et al. Utilized OpenStreetMap centerlines as labeled data and extracted roads from very high-resolution satellite images. Sun et al. Combined crowdsourced GPS data with satellite images to extract roads via CNN-based semantic segmentation. Zhou et al. Fused remote sensing images and GPS for road detection and extraction. Other learning-based approaches include Liu et al.'s multiscale residual neural architecture for road detection, Pan et al.'s fully convolutional neural network with VHR remote sensing, Matthias et al.'s estimation of road topology from aerial images, and Mi et al.'s generation of road lane graphs from lidar data using a hierarchical graph generation model. However, these studies exclusively focus on automobile road detection and extraction, neglecting the generalization or extension of the proposed methods to the pedestrian environment. In contrast, mapping the pedestrian environment has received relatively limited attention. Karimi et al. Explored pedestrian map generation approaches in a small-scale area, demonstrating preliminary mapping results that heavily rely on the availability and quality of input data. Recent advancements in remote sensing have led to more imagery-based approaches, such as Ametovic et al.'s detection of zebra crossings using satellite imagery and validation with street-level images. Gallardi et al. Classified and located crosswalks using an SVM classifier over data extracted from road maps, and Ning et al. extracted sidewalks from aerial images with a neural network and restored occluded segments from street view images. Other studies utilize on-the-ground data, such as Zhang et al.'s automation of street view image collection with auxiliary data to map sidewalk connectivity and sidewalk infrastructure. Howe et al. Extracted sidewalk paths using lidar data and point cloud segmentation. These methods often require physical systems to cover a large area to generate a pedestrian pathway network. Studies that map pedestrian pathway networks at scale are often based solely on existing street data. For example, Li et al.'s semi-automated method generated a sidewalk network using parcel-level data and roadway centerline, but it required human editing for quality control. The pedestrian Inferred system uses existing street network graph information to automate pathway network generation, but it only provides an optimistic hypothesis from incomplete information and does not capture the true connectivity. Recently, the Tiled 2 net system uses satellite imagery to segment sidewalks, crosswalks, and footpaths in cities, then simplifies the segmented polygons and extracts sidewalk centerlines. This work highlights the challenges of feature detection from only satellite imagery due to vegetation obstructions over the footpaths and the difficulties in correctly representing the path connectivity and routability when fitting centerlines to discrete polygons. Furthermore, various remote sensing datasets have been utilized for mapping, including the Toronto City Dataset, PRRS, the Deep Globe Dataset, and the ISPRS Dataset. These datasets enable researchers to study different tasks involving the use of aerial imagery data, but they do not provide pedestrian pathway graph annotations or a standard way to evaluate pedestrian pathway network extraction. The authors introduce the PathwayBench dataset, a large-scale dataset targeting the pedestrian environment, which addresses the lack of ground truth pedestrian pathway graphs with relevant features. This dataset provides annotations of connected, annotated pedestrian path networks represented as graphs, along with rasterizations of the graphs into pixel-labeled images for assessing segmentation-based algorithms. Additionally, it includes co-registered aerial imagery, annotated road networks represented as graphs, and rasterized street maps as input features. The dataset covers select regions in 3 U.S. cities, Seattle, Portland, and Washington, D.C., as well as regions in additional cities: Bellevue, Washington; Quito, Ecuador; São Paulo, Brazil; Santiago, Chile; and Valparaiso, Chile. The authors focus on U.S. cities in this paper to ensure fair comparisons across multiple methods. The graph annotations for pedestrian pathways are represented in the GeoJSON format and were collected and annotated through a standardized process involving mappers from the Open Sidewalks project. Each dataset sample includes aerial imagery, road networks, rasterized street map tiles, human-validated pedestrian pathway graphs, and rasterized pathways for supporting segmentation methods. The dataset also provides semantic segmentation annotations for 3 distinct classes: corner bulbs, sidewalks, and crossings. These classes are essential for semantically segmenting the pedestrian environment and are used as an intermediate step in many methods. The dataset is designed to be balanced and representative, including images from both North and South American urban contexts, to expand its ability to generalize to other regions and environments. However, the authors note that the lower-resolution aerial satellite images available for South American cities introduce an additional challenge for model learning. The PathwayBench dataset is a comprehensive collection of aerial imagery and annotations from diverse geographic areas, including North American and South American cities. It showcases varying levels of occlusion, such as sidewalks partially obstructed by buildings, shadows, and vegetation in aerial images. This dataset highlights the importance of incorporating multiple sources of input, like street map imagery tiles, to enhance segmentation outcomes, as demonstrated in Section 5. The concept of routability is introduced, which can be measured by the precision and recall of all paths in the built environment. However, the number of paths grows exponentially with the size of the graph, making it impractical to consider all paths equally. Instead, the authors focus on local routability by imposing polygons on the dataset and comparing local graph properties within each polygon to the ground truth. 4 measures of polygon-based routability are proposed: degree centrality, betweenus centrality, the number of connected components of the local polygon graph, and traversability. Traversability is a novel metric that assesses the ability to travel through small intersection-scale regions, allowing for meaningful comparisons across arbitrary graphs without requiring shared nodes or edges. This approach enables the construction of high-quality global routes from high-quality local routes, providing a more nuanced understanding of routability in the built environment. The paper highlights the limitations of traditional count-based metrics for evaluating the accuracy of pedestrian pathway graphs, particularly in capturing global routability and connectivity in city-scale graphs. To address these limitations, the authors introduce a new evaluation metric called traversability, which measures the ability to navigate from one boundary of a polygon to another using the graph. This metric is based on tessellating the space with polygons centered at intersections and comparing boundary-to-boundary traversal within each polygon between the ground truth and prediction graphs. The authors also define a pedestrian graph as a spatial pedestrian pathway graph representing the entire city region, introducing the concept of terminating nodes and polygon graphs. They provide a detailed explanation of how to construct a polygon graph and compute traversability using Jacquard similarity. This novel approach aims to provide a more comprehensive and meaningful way to evaluate the quality of predicted pedestrian pathways. The concept of polygon traversability in a graph G is defined as a pair of boundaries, G, I, G, J, being traversable if there exists a pair of nodes, U, V, such that U belongs to the node set of G, I. V belongs to the node set of G, J. U is not equal to V, and U is reachable from V in the polygon graph SG. The traversable boundary pairs of a polygon G in G are denoted as traversable pairs, G, G. A traversability metric is introduced to compare the sets of traversable boundary pairs for a polygon from a predicted pedestrian graph P and a ground truth pedestrian graph G using Jacquard similarity. The metric measures the size of the intersection of the traversable boundary pairs in G and P divided by the size of their union. The authors then describe the experimental setup for segmentation assessment with multiple inputs, including an aerial satellite image branch, a street map image tile branch, and both branches combined. The performance comparisons are shown in Figure 4, demonstrating the improvement gained from adding multiple input sources and the difficulty in predicting pedestrian path network classes with single source input. Assessing the performance of models in segmenting pathway graphs from aerial satellite images and street map images reveals that those using both input sources generate better predictions than those using only one input, as shown in Figure 4. However, pixel-wise measures, such as mean intersection over union, MIOU, are insufficient to evaluate the routability of the predicted graph. Instead, graph-level metrics, including local and global measures, are employed to assess the model's performance. These metrics, described in Section 4, include tiled 2net, pedestrian-FIR, and profit methods. The pathway network graph routability evaluation results for different cities, including Washington, D.C., Portland, Oregon, and Seattle, Washington, are presented in Table 2. The metrics considered include local, polygon-level routability metrics, count-based metrics, and F1 scores. The local metrics comprise average connected components, average between a centrality, and traversability similarity, which measures the similarity between local intersections in the predicted and ground truth graphs. The count-based metrics include node count, edge count, and average degree for the entire test area. The results show that the profit method, which uses pedestrian FIR to generate a hypothesis and then refines it using the rasterized street map and aerial imagery, outperforms the other methods in terms of local and global metrics. The profit method with different backbones, such as VGG16, DeepLab v3, and VIT, achieves high F1 scores and traversability similarity, indicating its ability to accurately predict pathway graphs. In contrast, the tiled 2net method, despite producing robust results in terms of edge count, fails to capture the local connectivity and structure of the ground truth graph. This highlights the importance of using graph-level metrics to evaluate the performance of models in pathway graph segmentation and underscores the strengths and weaknesses of different methods. The PathwayBench benchmark is a comprehensive evaluation mechanism for extracting pedestrian pathways from aerial imagery, addressing the inconsistency in datasets and metrics used in prior work. This benchmark includes 5 co-registered features for inferring high-accuracy pathway graphs and a suite of metrics tailored to assess graph structure and routability properties. Evaluation results show that tiled 2-net tends to overpredict disconnected edges, resulting in lower average betweenus centrality and lower traversability similarity scores. Conversely, the profit models, particularly those utilizing the VIT architecture, demonstrate better performance in graph routability, achieving higher traversability similarity values despite not having significantly higher F1 scores. The traversability similarity metric is found to be a more effective measure for evaluating graph routability, as it better aligns with the practical requirements of real-world routing and navigation tasks. This is in contrast to count-based metrics used in prior work, which do not capture the navigational experience of travelers. The PathwayBench benchmark effectively highlights the strengths and limitations of existing methods, which were previously obscured by conventional pixel-wise evaluations and simple edge counting approaches. By focusing evaluation on the experience of travelers, this work is expected to catalyze advancements in the extraction of large-scale pedestrian pathway networks. The work was funded in part by the Taskar Center for Accessible Technology, USDOTITS4US, and Microsoft's AI for Accessibility Award, with support from the G3 ICT organization for on-the-ground mapping efforts in several cities. The authors cite various research papers and studies related to pedestrian-centered data approaches, semantic image segmentation, and computer vision for urban infrastructure environments. Notably, Bolten et al.'s work on pedestrian-centered data approaches for equitable access to urban infrastructure environments highlights the importance of pedestrian-centric data collection for urban planning. The authors also reference Brandeis' algorithm for betweenus centrality, which is a measure of node centrality in a network, often used in graph theory and network analysis. In the context of semantic image segmentation, Chen et al.'s work on atlas convolution is cited, which is a technique used in deep neural networks for image segmentation tasks. The Deep Globe 2018 challenge focused on parsing the Earth through satellite images, emphasizing the role of computer vision in remote sensing applications. The authors also cite Dusovitsky et al.'s work on transformers for image recognition at scale, which introduced a vision transformer model that can process input images as sequences of patches. Several studies on crosswalk localization, sidewalk network mapping, and pedestrian accessibility assessment are referenced, including Gilardi et al.'s work on crosswalk localization from low-resolution satellite images, Hackley and Weber's OpenStreetMap project, Hosseini et al.'s scalable computer vision approach for generating sidewalk network datasets, and Howe and I's network-level sidewalk inventory method using mobile lidar and deep learning. The ISPRS test project on urban classification, 3D building reconstruction, and semantic labeling provides a benchmark for evaluating urban scene understanding methods. The authors also cite Zhou and Gebru's work on strategies for collecting sociocultural data in machine learning, highlighting the importance of considering sociocultural factors in data collection. Road network extraction from aerial imagery has been a topic of interest in various deep learning models and datasets. Previous studies have explored hierarchical graph generative models, such as HDMapGen, for high-definition map generation. Other approaches have utilized aerial and street view images for sidewalk extraction, and generic FCN-based methods for road network extraction from high-resolution remote sensing images. The importance of deep neural networks, specifically very deep convolutional networks, has also been highlighted. The fusion of crowdsourced GPS data with aerial imagery has been proposed for road extraction, while the issue of dataset bias has been emphasized, with a need for unbiased evaluation. The Toronto City Dataset, a large-scale, diverse dataset for urban scene understanding, has been cited as a valuable resource. Predictive inequity in object detection has been investigated, revealing performance differences across demographic groups. A method for road extraction from high-resolution images using weakly labeled OpenStreetMap centerlines has been mentioned. The paper also references an open and shared annotated dataset for learning urban pedestrian path networks, APE, and a method for collecting sidewalk network data at scale for accessible pedestrian travel. Notably, the authors introduce FooNet, a novel road extraction network that fuses location data and remote sensing imagery. This approach has the potential to improve road network extraction accuracy and robustness.